Suppose if you consider a charge, through surrounding the charge, it exerts some force. The area surrounding the charge up to which its influence is felt is called as your electric field. So, let us define about it in detail. So, next one is all about your electric field. So, what is electric field, children? The space around the charge up to which its influence is felt. Suppose if you consider a charge Q1, so surrounding the charge Q1, it creates some electric field. Surrounding the charge Q1, it creates some electric field. Suppose if you brought one more charge say Q2 is kept, when more charge Q2 is brought in this field, then the Q1 will exert some force on this Q2. Okay. So, Q1 will exert some force on Q2. Similarly, this Q2 will experience some force due to Q1. Some force due to Q1 Q2 experiences, and Q1 exerts some force on Q2 whenever the other charge is kept in the electric field generated by one charge. Okay. So, the space around a charge in which another charged particle experiences a force. Simply, the space around this complete space itself is called as your electric field. So, the space around a charge in which another charge experiences a force, another charge experiences a force is said to be having that kept in that electric field. Got it, children? Well, so now let us discuss in detail regarding the electric field intensity. So, the next one is all about your electric field intensity. So, what is electric field intensity? Electric field intensity at any point is defined as the force experienced by a unit positive charge at that point. So, electric field intensity, let us indicate with the letter E. So, electric field intensity is defined as the force experienced per unit charge. Force experienced per unit charge placed at a given point. And remember that this electric field is a vector quantity. Electric field intensity is a vector quantity. And units of this electric field is, so suppose in SI system if you consider, SI system, electric field intensity is measured in, force is measured in Newton and charge is measured in Coulomb. So, Newton per Coulomb is the SI unit of your electric field. Not only this, children. So, there are other units also in the SI system, not only Newton Coulomb. We know that work done is defined as force into displacement. Work done is defined as force into displacement, or force can be written as work done per displacement. So substituting the values. So for instead of force, we can also write it as units of work done is joule and S indicates displacement. So I'll change it. Force into displacement, or F is equals to work done per displacement. Units, work done units is measured in joules and displacement is measured in meters. So another unit of electric field is force is measured in joule per meter. Coulomb is measured, charge is measured in coulomb. So finally, the unit for electric field intensity is joule per meter coulomb. Joule per meter coulomb. Okay, or coulomb meter. So another unit is joule per coulomb meter. So this is another unit of electric field intensity in the SI system. Not only this, children, even it can also be measured in terms of volt. So another unit is also volt per meter. So this you will understand when I will be teaching electric potential. Okay. So there are three SI units for electric field intensity. One is Newton per coulomb, the other is joule per coulomb meter, the other is volt per meter. Okay. And remember that electric field intensity is always a vector quantity. It is a vector quantity. And the definition for this electric field intensity is that it is defined as the force experienced electric field intensity at any point. Electric field intensity at any point is defined as the force experienced by a unit positive charge placed at that point. Okay. So what is electric field intensity? Electric field intensity at any point is defined as the force experienced by a unit positive test charge placed at that particular point. Okay. So based on that, formula is given as E is equals to force experienced by unit positive charge. E is equals to F upon Q naught. Well, so let us suppose that this is a charge. Let this charge indicated with letter say some Q. Surrounding the Q we have electric field. Surrounding the charge we have electric field, something like this. And let us suppose that a charge say small q is kept. Positive charge is being kept in the electric field generated by the Q. Suppose if this happens to be a positive charge, then this is a positive charge and even the test charge, small unit positive charge also taken as plus Q. Then because of the both are same charges, like charges repel each other and the direction of the force will be away from that test charge Q naught. Suppose the same thing if the charge happens to be negative charge, then the force experienced by the positive charge will be in the direction opposite to that of the previous one, and this will be, it will be attracting force. Opposite charges attract each other. same charges repel each other. So, the force experienced by the unit positive charge kept at that point is defined as your electric field intensity. Okay, children. So, this is all about your electric field intensity. Now, let us try to understand in detail regarding the direction of electric field intensity. So, direction of electric field intensity is that, suppose if you consider different charges, okay. So, because if you consider a positive charge, attraction, positive charge if you consider, repulsion takes place, whereas if you consider a negative charge, attraction takes place. So, if both are positive charges, repulsion will takes place. Same thing, if both are opposite charges, then attraction may takes place. So, this is the direction of your electric field intensity. And suppose if you consider a negative charge, let us consider a negative charge, then the direction of electric field intensity on a test charge kept at its infinity will be towards this. This is the direction of your electric field intensity. Away from the positive charge towards the negative charge. This is all about the direction of electric field intensity. Always remember, children, electric field lines never form a closed loop. They start from positive charge and end at negative charge. Unlike magnetic poles, they never form a closed loops. So, what is a closed loop, children? So, we know that the positive charge and here negative charge. Always the direction of electric field intensity starts from positive charges and end at negative charges. Something like this. But they won't return back. They won't return back. Okay. So, if like suppose if you happens to be a magnetic pole, means north pole and south pole, they start from north pole, they go to the south pole and again inside the magnet also they go inside. So, this happens to be a closed loop. But here they won't come again back, just they start from the positive charge and end at negative charges. So, they won't form. So, like electric poles does not form a closed loops, whereas magnetic poles will form a closed loop. So, this is all about your closed loop. So, now also let us discuss in detail regarding one more concept, children, that is all about your electric potential. The next concept is all about your electric potential. So, moving ahead, okay. So, remember, just now we have studied that electric field intensity is a vector quantity, whereas electric potential is a scalar quantity. Electric potential is a scalar quantity. So, let us discuss regarding this electric potential in detail. Okay. The amount of work done in bringing a unit positive test charge from infinity to a given point. Let us suppose that if you want, this is a point, say A, where a charge to be brought, So, let us consider a test charge, say Q naught. Let us consider a test charge Q naught, which is somewhere very far away from the charge, whatever we have considered at A. Okay. So, this charge exerts electric field in and around its area. This charge exerts an electric field around its vicinity. Yes or no? As this is a positive charge, the direction of the electric field lines will be away from that. Now, what we are doing is that we are trying to bring this unit positive test charge to somewhere along this path, okay, against the direction of electric field. So, the work done, so we have to do some work to bring this unit a positive charge against the electric field experienced by it. Hence, the work done in bringing a unit positive test charge, I repeat, the work done in bringing a unit positive test charge from where? From somewhere at infinity. From infinity to that point along any arbitrary direction. So, maybe this direction, maybe straight line direction, any arbitrary direction. So, this is all about your electric potential. Okay. So, let me define the same, children. Definition of electric potential. The work done, it is defined as the amount of work done a unit positive test charge. The amount of work done in bringing a unit positive test charge from where? From infinity. So, what is the definition, children? Electric potential means the amount of work done in bringing a unit positive test charge from infinity to a given point against the direction of electric field intensity, okay, along any arbitrary direction. Got it, children? So, based on that, let us also go with the, remember that electric potential, it is a vector quantity. It is a vector quantity. Indicated generally with the letter V. So, the value of V is equals to, work done in bringing a unit positive test charge from infinity to a given point. Got it? Well, so units based on that, SI units of potential is, so generally potential is measured in volts. Potential V is measured in volts, or volt potential is nothing but work done per unit charge. So, V is measured in volts, or it can also be measured in work done per unit charge, means work is measured in joule and charge is measured in coulomb. So, joule per coulomb. So, the SI unit, you have two SI units, one is volt as well as joule per coulomb. Similarly, in CGS units, it can be measured in stat coulomb. CGS unit is measured in stat coulomb or ESU, electrostatic unit. Children, always remember that electric potential are again of two types. One is positive potential, the other is negative potential. Okay, two types of potentials are considered. One is positive potential, the other is negative potential. And potential due to positive charge is taken as positive potential, whereas the potential due to negative charge is taken as negative potential. So, two types of potential. So, that potential due to positive charge is generally considered as your positive potential. Whereas the potential due to negative charge is considered as your negative potential. That's it. So, before concluding that, let us try to find out the summation of potential due to not even single charge. If multiple charges are located, then how the effect will be on those charges. Let us discuss in detail. Okay, the last topic. So, potential due to a system of point charges. Potential due to a system of point charges. Well, for this, let us consider some system of point charges, say charge Q1, Q2, Q3, Q4 and also Q5. Let us also consider that this is a positive charge, positive, negative, positive and negative. So, on this test charge, we have considered at some point P, okay, at some point P, let us consider a test charge Q0. So, this Q0, Q1 is there. If you consider Q1, surrounding the Q1, you have some electric field. Okay, because of this electric field, some potential, some force is created on this charge. Okay, so force due to this charge on this Q1. Okay, so because of the presence of other charge, some potential exists between them. Similarly, if you consider the charge Q2, surrounding this, some electric field is there. In this electric field, the test charge is also there. Similarly, for Q3, Q4 and Q5. So, what we observed is that, well, let us suppose that this Q1 is at a distance of R1 from P, Q2 be at a distance of R2, Q3 at a distance of R3, Q4 at a distance of R4 and Q5 at a distance of Q5. Then the total potential at that point Q0 due to all the system of charges is written as V. The net potential is given by V equals to V1 plus V2 plus V3 plus V4 plus V5. That means potential due to first charge, potential due to second charge, potential due to third charge, fourth, fifth and so on. Okay. And remember children, the formula for potential is nothing but the work done per unit charge. Okay. So, work done per unit charge is also defined as, one second. Yes. First of all, let us try to give the formula for electric field intensity, which is not prescribed in your materials, but let me tell you. So, this electric field intensity formula is E bar is equals to F bar upon Q naught. But we know the formula for F as 1 by 4 pi epsilon, K times of Q1 Q2 by R square. What is the value of F? F is written as K times of Q1 Q2 by R square. So, K times of Q1, let us consider it as some Q. Q2, some test charge Q0 upon Q0. So, after simplifying, we get that the value of F is equals to K Q0, Q1 Q2 by R square. Q0 upon distance is some R. So, R square upon Q0. After simplifying this, we get the value of electric field intensity as KQ by R square. The value of electric field intensity is found to be KQ by R square. Okay. Similarly, suppose if you want to define the value of electric potential somewhere here. The value of electric potential is defined as work done per unit charge and it can also be written as force into displacement upon Q. Okay. And the value of force just now we have considered as K into charge Q, Q0 by R square whole upon Q0 into the distance. So, at what distance it is exerting means some R. So, similarly if you consider this, it can also be written as K Q by r square into r, or the value of V is found to be kq by r. The value of V is found to be kq by r. Hence, the formula for V as kq by r. If you consider the first potential due to first charge is given as V1. So, what is the formula? kq. What is k? Q instead of this Q1, and the distance is R1. R1. Charge is plus Q. Hence, this will be plus kq upon r. Similarly, if you consider this, I'll write it something like this, k q1 upon r. For V2, k positive charge, q2 upon r2. And here for V3, k charge is minus q3. So, minus q3 upon r3 plus, for the charge 4, we have k times of q4 upon r4 plus k times of minus q5 upon r5. So, the net potential due to the system of charges is given as something like this. The formula is kq by r, and the charges, sign of the charges are taken accordingly they have given. Okay. So, this is all about the potential due to a system of point charge. So, always remember, formula for potential is kq by r. Formula for electric field intensity is kq by r square. Whereas, the formula for force is found to be k times of q1, q2 by r square. So, let us try to remember these formulas, okay, and just go through them thoroughly so that we can apply for the solving numericals based on this concept. Okay, children, go through. Thank you.